Good morning, students. So I hope you can remember we were discussing about the complete randomized design, and we were discussing about how to analyze complete randomized design using one-way ANOVA. So in the last lecture, I gave you an example and I asked you to do some calculations and come. So before we work out with that example, let's go through some of the proofs so we can use those formulas to do our calculations. So when it comes to a complete randomized design, as we discussed in the last lecture, so there you have k number of treatments. So we are interested about actually one factor, and the levels of the factor, we call them as the treatments. For an example, if you take the if you can remember the example that we discussed about the teaching methods, so where you have 4 teaching methods, so teaching method is our factor, and since we had 4 different types of teaching methods, you had 4 treatment levels. So likewise, we take each level of the factor as a treatment. So in this case, if you just look at the design of the complete randomized, the outline of the complete randomized design, you can see here you have starting from 1, 2, 3 up to, let's say, k number of factors you have. So if you take factor 1, under factor 1, we can use several number of observations. So we call them as replicates. So to denote the number of replicates you have under factor 1, we take it as n1. So that is, let's say, if you take the teaching method example, let's say we are going to assign 4 students under teaching method 1, 2 students under teaching method 2. So when you take teaching method 1 as factor 1, you have 4 number of replicates. When you take teaching method 2 as the second treatment, then you have 2 number of replicates. Likewise, so to denote the number of replicates you have under each treatment, you take simple ni. So under first treatment, you have n1 number of replicates or observations. Under treatment 2, you have n2. Likewise, when you take treatment k, you have nk number of replicates. So when you take, if you take let's say the treatment 3 or the factor level 3, then if you want to if you look at this value, this is in this case you can see if you look at this one, this is coming from the third treatment. So here there's a small mistake. This should be x32. So if you take this one, it should be x3j. So you can see it's x3j. So that is the jth observation under factor level 3 or jth observation under treatment 3. So likewise, if you take it for the ith treatment, you can say if you take xi2, that is the second observation under ith treatment. So what you can do is, since we have different number of several treatments and different number of observations. So I told you during the last lecture, the number of observations you have under each treatment, it can be the same or it can be different. That doesn't matter in complete randomized designs. So what you can do is, first you can take the number of the summation of the observations under each treatment. So for an example, if you take treatment 1, if you take the summation of all these values, x11, x12, x1j up to x1n1, so that will give you the summation of all the observations under treatment 1. So that we denote as x1 dot. So if you take the summation of all the treatments under treatment K, that you can denote as xk dot. And then what you can do is we can calculate the mean of each treatment. So mean value of each treatment, what you have to do is if you calculate this total, you can divide it by the number of observations and calculate the mean. For an example, if you take treatment 1, here you have x1 dot, the summation is x1 dot, and here you have simple n1 number of observations. So if you take x1 dot, if you divide it by n1, you will get the mean. So mean under treatment 1, we denote it as x1 dot bar. Here you can see it's x1 dot bar. So likewise, if you take it for the ith treatment, the summation is xi dot, and you have n I number of observations. So if you divide xi dot by ni, you'll get xi dot bar. That is the mean under treatment I. So here are some notations you can see. So if you take xi dot, that is the summation of all the observations under treatment I. So if you just denote observation as xij, that is jth observation of treatment I, you have to take the summation of all these j values. J goes from 1 to ni, since under one treatment you have ni number of replicates. So if you take this total and divide it by ni, that is the number of observations you have under treatment I, you get the mean value. So if you take the total of all these observations, so if we know we denote an observation as xij, so where j can go from 1 to ni, and if you take I is the treatment index. So we have k number of treatments. I can go from 1 to k. So if you take the total of all these observations, you get the overall total. So we call it as the grand total, which is denoted by x dot dot. And if you take the grand total, if you divide it by number of observations in the under the experiment, that is total number of observations. If you take the total number of observations, we know under one treatment you have simple ni number of observations. So you have k number of treatments. So if you take the summation of all ni's starting from 1 to k, you get the total number of observations. So let's say it's equal to capital N. So if you divide this grand total by capital N, you'll get the overall mean. We call it as the grand mean and denote it by x dot dot bar. So you can use whatever the letter you like, y, o, x, o, but same notation you have to use. If you are using y, this is y dot dot bar. That is the grand mean. So in this case, so we actually discuss about two models, two mathematical models, the treatment mean model and the effect model. So in this case, if you if you can remember, when you take the treatment effect model, in the treatment mean model, you have xij, which is equal to mu I plus the error term. But when it comes to treatment effect model, we have our observation xij, where it is equal to mu plus tau I plus the error term. Here, the tau I is the effect of the ith treatment. So in this case, if you take this tau I, when you compare the two models, when it comes to the treatment mean model, here to replace this term mu plus tau I, we have mu I. So when you compare the two models, so we can see mu I is equal to mu plus tau I. So actually, there's one thing we can see when if you just check the treatment effect of each and every treatment, and if you take the summation, it's always adding up to 0. We can easily prove that. Now we can see when you compare the two models, we know mu I is equal to mu plus tau I in the treatment mean model, we have mu I plus the error. Here we have mu plus tau I. So since the two models are the same, so we can equal mu plus tau I term to mu I. So in that case, if you can write an expression for tau I, that is tau I is equal to mu I minus mu. So since we have k number of treatments, we can take where I goes from 1 to k. So you can see if you take the summation on your left hand side, we can take the summation of your right hand side. And then here we have mu I minus mu, where I goes from 1 to k. Then in this case, if you take the summation separately, here you have I goes from 1 to k mu I minus. Mu is a constant. Since we have the index from 1 to k, we can write here k times mu, since mu is a constant. And then the first term, we can rearrange this. So I'm going to multiply this first term by k and divide it by k. So if you just keep k here, and if you take summation I goes from 1 to k mu I divide by k, that is, you are taking the summation of all the means and divide it by the number of treatments. So that is, again, you get the overall mean value. So that you can write it as mu, but here you have k. So that is k times mu minus, here we have already k mu. So we can see k mu minus k mu is equal to 0. So for any, it doesn't matter how many number of treatments you have in your design. When it comes to complete randomized design, if you take the summation of the treatments, treatment effects, it's always adding up to 0. Do you all understand?
Yes, madam.
Okay. Now during the last lecture, I actually just showed you the example that we are going to discuss. And I just said that we can calculate this treatment mean and the overall mean, and I asked you to do those calculations and come. But if we are going to analyze the complete randomized design using one-way ANOVA, what we are going to do is actually we have to construct the Anova table to analyze this complete randomized design. So in this case, when it comes to this complete randomized design, so we know we have, if you take the treatment effect model, or if you take the treatment mean model, so there we have some parameters to estimate. So in order to estimate the parameters, when it comes to complete randomized design, you can use the least square method, or else you can use the maximum likelihood method. Any method you like, you can use. So in this case, we are going to illustrate the estimators using the least square method. Since for the simple linear regression and the multiple linear regression, we were using this least square method to estimate our parameters. So in the complete randomized design also, we are going to use least square method, but it's not a must. You can use any other method like maximum likelihood to estimate your parameters. So we know when it comes to the least square method, what we do is we always take the squared summation of the error terms, and we are trying to minimize the squared summation of the error terms as much as possible. So then we are going to find out the estimates at the point which we get the minimum value for our squared summation of errors. So in this case, if you take the error term as epsilon ij, so we know for under each treatment, we have ni number of observations, where j goes from 1 to ni, and we have k number of treatments, so I goes from 1 to k. So when it comes to least square, now we have to take the squared value of this error. So if you take the model if we are using the treatment effect model, we know xij is equal to mu plus 2i plus the error term. So if you take the error term, that is you have xij minus mu minus 2i, and we have to take the squared term of this. So we can see we have two parameters to estimate, that is mu and 2i. So what we have to do is, under least square method, after writing down an expression for the squared error terms, we can partially differentiate the equation. So let's differentiate this equation first by mu. So you can see here you have this term to the power 2. So we can write 2 times this term xij minus mu minus 2i. But if you take mu, you have minus 1 as the coefficient. So you have to multiply this by minus 1. So you have minus 2 times xij minus mu minus 2i. So what you can do here, you have I goes from 1 to k and j goes from 1 to ni. So you can equal this term to 0, and we can take one equation from that. And if you take this and if you partially differentiate this one by 2i, in this case, again, we can see if you differentiate this by 2i, we can see again 2 times this term xij minus mu minus 2i. And if you look at the coefficient of 2i, again you have minus 1, so you have to multiply this by minus. So you have minus 2 times, since for the 2 you have index I, so here we can use only the index j. So j goes from 1 to ni, and you have this term where that's equal to 0. We can take that one as our second equation. So we can take the additional constraint, that is ni to I is equal to 0. In this case, we are going to use these 3 equations to find out the estimators for our parameters in completely randomized design. So in this case, let's take the equation 1. So if you take the equation 1, if you divide both sides by minus 2 will cancel out. Then you have the 2 summations xij here is equal to, here you have minus mu and minus 2i. So you can take these 2 terms into your right hand side. So in that case, we can write mu into, you have summation I goes from 1 to k, summation j goes from 1 to ni times 1 plus the 2 summations times 2i. So in this case, if you take this second term, which is on your right hand side, here you have j goes from 1 to ni to I. So this one you can replace, since you have the index from 1 to ni, you can replace this one as ni to I. And when you replace this term by ni to I, we know from the constraint ni to I summation is equal to 0. So this term will be equal to 0. And here you have mu. And here, if you look at the summation, it goes from 1 to, j goes from 1 to ni. I goes from 1 to k. That is, we are taking the total number of observations. So here under CRD, let's say we have capital N number of total observations. So that is capital N. So since we are going to find the estimators for our parameter mu, let's denote mu as mu hat. So here we have summation I goes from 1 to k, summation j goes from 1 to ni, xij is equal to mu hat times n. So we want to find an estimator for mu hat. So mu hat is equal to summation xij divided by n. That is, we are taking the grand total and divided by the total number of observations. That is, that is equal to the grand mean. So we can denote it by x double dot bar. So we can see for the mean, we can use x double dot bar. as an estimator. So if you take the second equation here, if you use this second equation, if you divide both sides by -2, here you have summation j goes from 1 to ni, xij minus mu minus 2i is equal to 0. So if you take that one, if you take this equation, you can see, so in this, on your left hand side, you can keep xij, where j goes from 1 to ni. And here you have mu hat. And here you have j goes from 1 to ni times 1. That is, we have ni number of values here. So you have here ni plus here 2i hat summation, where j goes from 1 to ni. So tau I is independent from the index j. So here you can write this as ni. So in this case, if you just write down an expression for tau I hat, you can keep tau I here, and you can just bring mu hat in I term to your left hand side. So you have summation I goes from 1 to ni, xij minus mu hat ni. So when you divide mu hat ni by ni, you get mu hat. And for the first term, you have xij, where j goes from 1 to ni divided by ni. So that is, you are taking the, since j goes from 1 to ni, you are taking the total of all the observations under treatment I, and you are dividing it by the total number of observations under treatment I, where this is equal to the mean of the treatment I, which we can denote by xi dot bar. So you can see tau I hat is equal to xi dot bar minus mu hat. So this is how we can use the least square estimators in order to estimate the parameters in complete randomized design. So this is for the treatment effect model, but when it comes to treatment mean model, we know we have only one parameter, mu I, and mu I is equal to mu plus tau I. So if you know the estimator for mu and tau I, we can just easily find what is the mu I value. So in that case, you can use this least square method like this to estimate the parameters of the complete randomized design. And as I told you, now we are going to use one-way ANOVA to, we are going to construct the Anova table to analyze the complete randomized design. So in that case, we know when we use the Anova table for simple linear regression, for the multiple linear regression, we had to find out the total sum of squares, the error sum of squares, the regression sum of squares, the degrees of freedom. So all those things we have to perform under CRD as well. So if we want to find those values, first thing that we have to do is we have to find out expressions to find out the total sum of squares, the error sum of squares, and the regression sum of squares. So let's take the total sum of squares. So we denote it by SST. So I have told you earlier also, you can use different notations, whatever the notation which is comfortable with you, you can use. So when you take the total sum of squares, in the total sum of squares, we are looking for the total variation. So we take one observation and we take the grand total and we observe the difference between the observation and the grand total. So here the observation is denoted by xij minus the grand total, we know it's denoted by x double dot bar. So since we are interested about the squared value, you can take the squared term, and we know j goes from 1 to ni. We have ni number of observations under one treatment, and I goes from 1 to k. So let's expand this equation and see. So if you want to take this squared value, what we can do is, let's rearrange this one. So we have xij here and we have minus x double dot bar. So what we can do is here we can subtract xi dot bar and add xi dot bar to this term. So if you consider this first term as one term and these two values as the second term. So here if you are taking the squared value, this is now in the format a plus b to the power 2. So here you have xij minus x dot bar squared. Then if you take xi dot bar minus x double dot bar squared, and you have the summations, and then you have to take 2 times the summation of these two terms. So here you have to add plus 2, that is missing here. You have to add plus 2 times summation of xij minus xi dot bar into xi dot bar minus x double dot bar. So let's look at this summation and see what will happen here. So if you take this value, we can see here we have xij minus xi dot bar into xi dot bar minus x double dot bar, where you have j goes from 1 to ni, I goes from 1 to k. So if you just rewrite this one, if you just observe this term, xi dot bar minus x double dot bar, you can see it's independent from the index j. So let's keep it here. And so we have I goes from 1 to k, xi dot bar minus x double dot bar. So here we have j goes from 1 to ni, xij minus xi dot bar. So if you look at this term, now in this case, if you take j from 1 to ni for xij, that is, you are taking the total of all the observations under treatment I. That you can denote as xi dot. And in this case, here you have xi dot bar, and it's independent from the index j. So you can write this as ni times xi dot bar. So we know xi dot bar is equal to xi dot divided by n. So xi dot divided by ni. So ni times xi dot bar you can replace by xi dot. So this term will become 0. That is we can write this whole term, the multiplication of these two terms, that they are equal to 0. From that, actually we can find, now here you can see we have the total sum of squares, they are equal to xij minus x double dot bar. And in this case, we have error sum of square values, that is equal to xij minus xi dot bar squared. And the regression sum of square, here we have xi dot bar minus x double dot bar squared. So if you look at this one, the regression sum of square, you can see it's independent from the index j. So you can write this summation where I goes from 1 to k, ni times xi dot bar minus x double dot bar squared. So we are going to use these terms in order to find out, analyze the complete randomized design. So in this case, we can see here you have the total sum of squares, that is equal to sum of squares error and also sum of squares regression. So in this case, the sum of squares regression means the sum of squares due to the effect of the treatments, and the error, it's the same, that is the sum of squares due to error. So in this case, since we don't have a regressor, we have treatment. So this SSR is coming from the treatments. So in this case, so when we are going to construct the Anova table, what you have to do is we have to first write down the hypothesis that we are going to test. So since we have two models in CRD, you can use whatever the model which is easy for you. So if you are going to use the treatment mean model, so the H naught is all the treatments are equal. That is mu1, mu2, mu3 up to mu k. All the treatments are equal. H1 is at least two pair of treatments are not equal. That you can write mu I not equal to mu j at for any given ij value where I and j are not equal. That is, at least one pair of the means are not equal. And if you're going to use the treatment effect model, you can write down your hypothesis using tau I values. That is, your H naught is tau 1 equal to 2 up to tau k equal to 0. That is, all the treatment effects are equal and equal to 0. And in this case, if you take H1, that is tau I not equal to 0 for at least one I. That is, at least one treatment effect is not equal to 0. So you can write whatever the hypothesis that you would like to test. If you are going to use the treatment mean model, you have to go with the first one. If you are going to use the treatment effect model, you have to use the second one. And so before this, I'll show you the Anova table. Yeah, so this is the Anova table. So in this case, when it comes to Anova table, now we have the total sum of squares. So if you look at the total sum of squares, the degrees of freedom, you have to take the total number of observations minus 1. And then we have SSR, that is the sum of squares between the treatments. And here you have the expression which we already derived. And when it comes to the degrees of freedom, that is equal to k minus 1, where k is number of treatments. So when it comes to error, what you have to do is, after calculating the total of and total sum of squares and the treatment sum of squares, you can take the difference and calculate the error. Or else, now we just derived the equation, you can use that one as well. And when it comes to the degrees of freedom, that is equal to n minus k. That is, from the total number of observations, you have to subtract the number of treatments. Number of treatments you have in your model. And then you have to take the mean square value. That is, you have to take the sum of squared values and divide it by the respective degrees of freedom. For an example, when it comes to treatment, you have the sum of square, the degrees of freedom is k minus 1. So this one you have to divide it by k minus 1. And when it comes to SSE, the degrees of freedom n minus k. So you have to take the sum of square and divide it by n minus k. So then what you have to do is, you have to take the mean square two mean square values and divide it, take the ratio, and then that will give you the f value. And this f statistic is having this, actually this statistic is having a f distribution. So we can see the numerator's degrees of freedom is k minus 1, denominator's degrees of freedom is n minus 2. So the calculated f value, we can just check with the calculated f value, we can just compare with the table value. If the calculated value is greater than the table value, we can reject H naught. So this is how we construct the Anova table. We'll do one example and see, then you will understand. Do you have any questions? Okay, then I will share you. Let's do the calculations and see. Okay, I hope you all can see my screen. So this is actually the data set that I gave you during last lecture, the exercise that I asked you to do some calculations for homework. So if you can remember, in this case, an engineer is interested in determining whether the percentage in fiber affects the tensile strength. Then the engineer run the experiment with 5 levels of cotton percentages and 5 replicates for each level. Tests the hypothesis that cotton weight percentages affect the tensile strength of the fiber. So here what I have done is in order to do the calculations, I have, yeah.
We can't see the screen.
Okay. Let me share again. Now can you all see?
Yes, ma'am. Now.
Okay, right. So this is the example that we, this is where we stopped during the last lecture. So in this case, I have copied all these values to an Excel sheet just to illustrate the calculation. So in this case, you have, we are going to find out whether there is any effect for the strength when we change the percentage of the cotton in this fiber. So they have chosen 5 different levels of cotton percentage, and under each percentage, they have observed 5 replicates. They have observed the strength, and then we have the value. So we have to check whether there is any difference. So in this case, the first thing that you have to identify is here we have only one factor. That is the cotton percentage. In this case, we are interested about the cotton percentage, whether the cotton percentage has any effect towards the strength of this fiber. So in that case, I have taken the cotton percentages, since there are 5 different cotton percentages, as 1, 2, 3, 4, and 5, the 5 different cotton percentage. So if you take the first cotton percentage, under that they have 5 observations. So they have observed the strength. So that is, if you use the first percentage of first cotton percentage value, the first observation has a strength of 7, again 7, 15, 11, and 9. When you take the second cotton percentage value, so under that again you have 5 replicates, 5 observations, and the strength values are 12, 17, 12, 18, 18. So this is your design. So these are your treatments. So the columns are your treatments. So first you have to identify what are your treatments when you perform this manually in your examination. So when you have your treatments, first thing that you can do is under each treatment, you can calculate the total, the summation of the observations and the mean value. So let's do that. If you take the first treatment, if you take the summation of all these 5 observations, it will give you the summation of the first treatment, summation of the observations of the first treatment. So we know the summation of the observations of the treatment, we can denote it by yi dot, right? So if you take the first one, I'm going to take the summation. So let's take the summation of these first 5 values. So likewise, what you can do is you can do the calculate the summation of all these values. So that is yi dot values I have. This is the summation. So when you take the summation under first treatment, that is 49. Summation of the observations under second treatment, 77. Likewise. So if you know the summation of each treatment or summation of the observations under each treatment, we can divide it by the number of observations to calculate the mean. Now in this case, we can see under each treatment, you have 5 replicates. So what you have to do is we can take the total and divide it by 5 to find out the mean value. So here we get the mean values. So when you do it manually, first calculate the total of each treatment and then divide it by the observations, number of observations under each treatment to calculate the mean of each treatment, which is denoted by yi dot bar. So now we have yi dot bar values. So in that case, if we want to calculate y double dot value, that is the grand total, we know we have to take the total of all these observations. And now we have the total of each treatment, total under each treatment. So what you can do is to calculate the grand total, you can just take the total of these values. That is the total of the observations under each treatment. If you take that total, that is adding up to the grand total. So now what you have to do is here, after calculating the grand total, we can calculate the grand total is denoted by y double dot, and then we can calculate y double dot bar. So that is grand total divided by the number of observations under the experiment. So we can see under one treatment you have 5 replicates and we have 5 number of treatments. So altogether we have 25. So what you can do is, now the grand total is 376. We can divide it by 25. So this is the grand mean. Now we know the grand mean value, grand total, and the treatment mean values and the treatment total values. So to construct the Anova table, now these are the equations that we just derived. So if you look at the total sum of squares, we have yij minus y double dot bar squared value. So what you have to do is you have to take each and every yij and then you have to subtract the grand mean and take the squared value and take the summation. So first I'm going to take these yij values. I'm going to copy them and I'm going to put them into one column since that is easy to do for the calculations. So here I'm going to take the first row and put it here. You can copy the whole matrix and do, but I'll show you one by one, since when you do it manually you have to do it in this way. So this is the second one. Okay, or else we'll do like this. Here I'm going to take the first column, that is all the observations under treatment 1. I'm going to paste it here, and all the observations under treatment 2. I'm going to paste it here, and all the observations under treatment 3. I'm going to paste it here, and all the observations under treatment 4. I'm going to paste it here, and finally we have all the observations under treatment 5, and then I'm going to paste it here. So altogether we have 25 observations. You can just recheck the count. See, we have 25 observations. Now from each and every observation, what you have to do, you have to subtract the grand mean. So that is, you take the observation, subtract, the grand mean is 15.04. 15.04. And then we have to take the squared value of this. So you take the grand mean and subtract that from the observation and then take the squared value. So we have to do this for all the observations in our data set. Since I'm using Excel, that's easy. So when you're doing this in the exam, you have to do this manually for all the observations. And now I'm going to take the summation of these squared values. So you can see summation is 636.97. So I'll write it somewhere here. When you take SSTO, here sum of squared values you have. Sum of square value is 636.96, close to 637. So now to construct the Anova table, now we have to calculate the treatment value, or we have to calculate the error. Whatever is easy for you all. I'm going to calculate the error. So if you're going to calculate the error, what you have to do is from each and every observation, you have to subtract its treatment mean value. That is, when you take the first 5 observations under treatment 1, you have to subtract here. Now, when you take the first 5 observations of treatment 1, you have to subtract the mean value of that. That is yi dot bar from the first 5 observations, right? So here, let's do that. So I'm going to just color. These are the first 5 observations, and then here we have the next 5 observations, and this is the third treatment, and then we have the 4th one, and again we have the 5th treatment, right? So I just color coded since that's easy to see, right? So for the first treatment, for these first 5 observations, the yi dot bar value, that is equal to 9.8. So I'm going to put 9.8. And for the first 5 observations, I'm going to put 9.8 as yi dot. And for the second treatment, that is 15.4. That is 15.4. So I'm going to put 15.4 for the next 5 observations. And then we have 17.6. 17.6. So let's take 17.6 for the next 5, and then 21.6. So here we have 21.6. And if you check the treatment mean for the last treatment, that is 10.8. So we can put 10.8 here. Okay, so now what we have to do, we have to take the difference between Yij and this treatment mean. So that is Yij is this minus, this is the treatment mean. And then what you have to do is you have to take this difference. And then what you have to do is you have to take the squared value of this difference. So, and then you can take the summation of these squared values. So I'm going to take the summation of the squared values. You can see that is equal to 161.2. So when it comes to so Anova table, we have SSR, SSTO, and SSE. So the SSE sum of squares are the ones that we calculated right now. That is 161.2. So for SSR, to calculate, you can take the difference between the total and the SSE value. So that is 475.76. And then we can calculate the degrees of freedom. So I told you when it comes to the total, the degrees of freedom is equal to capital N minus 1. So that is the total number of observations minus 1. That is, here we have 25. So it is 25 minus 1. So you can put 25 minus 1 here. And then when it comes to the regression sum of square, that is under treatment, that is equal to k minus 1. So that is K is the number of treatments you have. So in this particular one, you have 5 treatments, right? So this is equal to K minus 1. So here you have 5 treatments. So that is 5 minus 1. This is equal to 5 minus 1. Right? So this is 5 minus 1. And then under error, you have to take the total number of observations minus the number of treatments as the degrees of freedom. So that is, you have capital N is 25. You have 5 number of treatments, 25 minus 1, 20. So we have the degrees of freedom. And then we have to calculate the mean square values. So for the SSR, what you have to do is you have to take the sum of square value divided by the degrees of freedom. And for the SSE, you have to take the sum of square value divided by its respective degrees of freedom. And then you can calculate the F value. So to calculate the F value, what you have to do is you have to take the SSR, you have to calculate the regression mean square MSR value divided by MSE value. So you can see the calculated F value is this, that is 14.75. Now we have to calculate this with the table value. So we can see when you take the numerator, degrees of freedom is 4, denominator's degrees of freedom is 20. So that is, you have to check for the F table with these values, where alpha is equal to 0.05, and check what is the table value here. So in this case, so I'll show you. So when you're doing this calculation, so you can use this formulas just as I explained to do the calculation, or else we can just take these formulas and rearrange, and we can find these alternative formulas to do the calculations. That is, for an example, when you want to calculate SSR, that is treatment sum of squares, you can use xi dot squared divided by ni minus x double dot squared divided by capital N. Here I have given the proof. So you can use this equation if you want to calculate the treatment sum of squares. Likewise, for the total sum of squares, you can use this alternative formula. So whatever the formula is easy for you, you can use. So in this one, so just as I explained, we are doing this manually. The first thing is you have to write down the hypothesis like this, where if you are going with the treatment mean model, you can write all the treatment means are equal to 0, or mu ij is not equal to mu I is not equal to mu j for at least one pair. Or if you are going with the treatment effect, you can write to 1 to 2 up to here. Since we have 5 treatments, to 5 equal to 0. Now you can see the difference when if you are comparing the means, you have to check whether all the means are equal. But if you are comparing the treatments, you have to check whether all the treatments effects are equal to 0, right? So you have to first write down this equation, the hypothesis. And here I have used the alternative formula to do the calculations. You will see you get the same answer. See, we got the total sum of square 636.96 and the error sum of square as 162.2. So when you calculate the treatment sum of square, that is 475.76. And then we get the ratio F value 14.75. So when you check the table F value, you will see when you check the table F value, that is equal to 2.8661. So our calculated value is 14.757. So that is greater than the table value. So that is we can reject H naught. So if you are rejecting H naught, that is we don't have enough evidence to say that all the treatment means are equal to 0. All the treatment means are equal, or the treatment effect is equal to 0 under 5% level of significance. So this is how you perform a CRD using a given data set. So in the exam also, when I give you the data set, you should be able to perform this CRD like this. Okay, up to that, you have any questions? Do you all understand?
Yes, madam.
Okay, then now I'll show you how to perform this CRD using R. So let me share the console. Okay, right. So here, first thing that you have to do is when you are using R, first you have to save, you have to just enter all the values to an Excel sheet, and then you have to save it as a CSV file. So by now you know that. So I have already saved my Excel file. And then I'll show you, I'm going to import my Excel file to R. So let's say my file, I'll give a file name as my data. So I'm going to use read.table. So I'm going to use read.table function, that is file.choose header equal true. So first I can select my file from where I have saved. So this is my file. Okay, so now I'm going to check whether I have the correct, whether I have selected the correct file to R. Give me a second. I think there's something wrong with the file. I'll just double check. Let me select my file again. I think there's something wrong with the file that I have selected. Yeah, so here this is the file that I have selected. So you can see we have 5 treatments. Under one treatment, we have 5 replicates. So we have import all the data to our to do our analysis. So first thing that you can do is, once you are going to analyze a complete randomized design, after importing your data, first thing you can graphically check whether there is a difference between these treatments. You see that for that purpose, you can use a box plot. So what I'm going to do is I'm going to use the box plot command. That's box plot. So you can see my first treatment is denoted by x1. So my data set name is my data. So I'm going to give the my data $mark x1. So the box I can get the box plot with respect to x1 in my x1 variable in my data set. So likewise, I'm going to take the box plot with respect to each and every treatment. So you can see now when you run this command, you will see the box plots under each treatment level. So when you actually observe the box plots also, you can see the treatment means are different. Their distributions are different. So in this case, this is first to analyze graphically the effect of each treatment. So when you observe this, you can just write down the distribution of under each treatment is different. So some of the treatments are having outliers as well. So this is just to get a basic idea about our treatment levels. And then what I have to do is, when you're going to analyze this first, the first thing that you have to do is you have to put all these data, all these values into one column. And then you have to say this 7 is coming from first treatment, 12 is coming from second treatment. Likewise, for each and every data point, you have to tell from which treatment these observations are coming. So for that, what I can do is first I can concatenate all these rows into one matrix, one column. So to do that, I'll take that column as R. So what I'm going to do is I'm going to use this function to concatenate these rows in my data frame. That is function T as dot matrix. And then you have to give the name of the data set that you want to concatenate. So I'm just going to call R and C. So you can see here, they have put all these values into one row. You can see it has converted into a row vector. So the first row you have 7, 12, 14, 19, 7 and 7, 17. Likewise, all these rows have been concatenated to one row. And then now I have to label each and every observation. Likewise, the first one is coming from the first observation, 7 is coming from the first treatment. Likewise. So what I can do is I'll take, let's say F. So F is just a character vector to give the treatment names. Let's say treatment 1. Let's say treatment 2 you have. Then let's say treatment 3, treatment 4, and treatment 5. So here These are the names of my treatments. And in this case, we know when it comes to a complete randomized design, the treatment number is denoted by K. So in our case, we have 5 number of treatments, and under each treatment, we have 5 number of replicates. If you take the number of replicates as n, we have 5 number of replicates. So now what I have to do is, now for each and every for each and every item in my row vector, I have to give these treatment names. So to do that, I'm going to use a function called GL. So that is treatment names I'm going to give using this GL function. So first you have to give for the GL function, you have to give the number of treatments you have. So we have already assigned the number of treatments from K, and from 1, starting from 1 to n into K, because we have total number of n is 5, K is again 5. So starting from 1 to 25, we have to assign these treatment names to our row vector values. So that we are going to use factor these values. So if you just call this TM, you will see they have used T1, T2, 3, T4, T5. Likewise, they have repeat this 5 times. That's what we do here. Now we can run the ANOVA using this design. So I'm going to give a variable name as AV, and to run ANOVA, we are using the built-in function AOV. So our data is in this row vector R, and then we have to give the factors as TM, the ones that we have already labeled. So I'm going to use summary AV. Here you will see the Anova table. You can see here the treatment SSR is 475.8. That's the value that we received. And SSC 161.2. We exactly received these 2 values. And here they are not giving the total, but you can just take the total of these 2 and calculate SSTO. And if you look at this value, here you have the F value, and they have given the P value as well. So you can see P value is very small, and this is significant. So that is, we can reject H naught. And here you have 3 stars. So that is under 0% significance level, you can reject H naught. So that is, this is highly significant. So that is, all the treatments are not equal, or else you can say all the treatment effects are not equal to 0, or all the treatment means are not equal. There's a difference between these treatments. So actually, in this case, when you find there's a difference between these treatments, now in this case, when you want to, since we are interested about the strength, so if you want to take a decision about, now let's say if you are the engineer, now you want to select the best cotton percentage for your fiber. So in that case, now we already know the due to the cotton percentage, the strength is different. So in that case, we have to decide what is the best cotton percentage level that you have to use. So for that, we can use this mean effect plot and just see under each treatment which gives the highest mean. Since we are interested about the strength, we can check under each treatment which gives the highest strength value. So to do that, we have to install several packages to obtain that main effects plot. So to do that, we have to use package car. So it will take some time. Okay, and we want package car data as well. So we have to install these two packages. And also I'm going to install another new package that is FIA. So I'm going to select that package. So I'm going to select India from this, which is the closest country for us. Sri Lanka is not in the given list. And then I'm going to select this package. Yeah, this is here, and this so after that, I'm going to load this package here. Yeah, and then after that, I'm going to use this function interaction means, which will give you the means effect plot. So here you have to give the name of the model, that the name of the Anova model. So here I have used AV as the name of the Anova model that I have fitted. And here I will give a name for this variable name. Then you can use plot, the name of this variable, that is IM. Now you can see the mean effects plot. So you can see, if you just observe this, you can see under treatment 4, you have the highest mean, highest strength. So in that case, if you want to select the best cotton percentage, which gives the highest strength, since the strength values are different under each treatment, we can select treatment 4, the cotton percentage under treatment 4. But if that is very expensive, what you can do is, you can see there is only small difference between treatment 2 and treatment 3. So we can go to treatment 2 or treatment 3. And also we will learn in the next coming up lectures whether to check whether actually these two treatments are different or the same. Anyway, by obtaining this mean effect plot, you can just get an idea about each treatment level. Okay, so do you have any question up to that point? Okay, so I hope that you understood. So please go through the calculations manually. Since I'm doing this online, I used Excel, but in your examination, you have to do that manually. So please go through all the calculations. So if you have no questions, I'm going to stop from this point. Okay, so we'll meet again tomorrow. Have a nice day and thank you.